So in his wonderful PLDI keynote earlier this year, Emery Berger gave this wonderful Simpsons themed talk where he joked about making a talk with AI generated images. So I did. So OCaml 5.0 is the next major release of the OCaml programming language. It brings in native support for concurrency and parallelism to OCaml. So by concurrency, we mean overlapped execution of tasks in time. And we define parallelism as simultaneous execution of tasks overlapped in time. So we have this separation between concurrency and parallelism in OCaml 5, and we provide distinct mechanisms for expressing concurrency and parallelism. For concurrency, we express them through effect handlers, as Sam mentioned. And for parallelism, we have a primitive called domains. So in this talk, I want to tell you about how we got from sequential OCaml 4 to this parallel OCaml 5 through the Multicore OCaml project, which I had led. So this journey wouldn't be fun if there wasn't any adventure and we had our fair share of adversaries. So what I want to sort of tell you in this talk is the challenges that we had faced in order to retrofit concurrency and parallelism to an industrial strength language like OCaml and how that shaped our approach. And possibly also tell you about some of the takeaways that you can take away from this multicore OCaml experience if you were designing your own programming language abstractions and you were brave/foolish enough to retrofit them onto industrial strength languages. So I've split the talk into two. I'm going to first talk about the journey to OCaml 5, and then I'm going to sort of tell you about the takeaways. So let's go back to the year 2014. So OCaml was an 18-year-old industrial strength functional programming language that was reasonably popular within the industry and academia. So OCaml was particularly favored for low latency network systems, program analysis tools, compilers, proof assistants, and whatnot. But when compared to systems programming languages that were out there, OCaml was one of the few that did not have multicore support, right? So to be clear, OCaml had threads, but when you have multiple threads, only one of them can execute OCaml at any point. Essentially, you had a big runtime block around the heap. The other threads could be executing C code in parallel. So this is no different from Python, which has a global interpreter lock. So the primary goal of Multicore OCaml project was to eliminate this runtime lock and allow multiple OCaml threads to run at the same time. So Sam Gross at Meta, who is one of the developers of PyTorch, is also working on a project with similar goals for Python, which is to remove this global interpreter lock. So in this undertaking, we had a number of challenges. So the first challenge is that OCaml was heavily used by the time we started this project. There were millions of lines of OCaml code in production, right? And none of this code was written with concurrency and parallelism in mind. Right? And even after we add concurrency and parallelism to OCaml, most of this code is likely to remain sequential. And if you were a developer, you were maintaining thousands of lines of OCaml code, and I came to you and told you, hey, you can have concurrency and parallelism, but you have to modify all of your code. This is not going to fly. So the first requirement that we had for this project is that we were not going to break existing code. Right? So OCaml is particularly favored for low latency GC and having a predictable performance. If you have an application that can tolerate 10 millisecond latency, then OCaml is a great language for you. So in designing this parallel extension, we wanted to ensure that we can preserve this GC latency before focusing on parallel scalability, right? And ordering these goals in this order also makes, also influences how we design the garbage collectors. Finally, OCaml core team is composed of volunteers. So in building this multicore OCaml project, we didn't want to write thousands of lines of code, throw it across the wall and disappear. So essentially what we wanted to do is to ensure that the burden on the OCaml core developers remains small. One of the One of the things that we wanted to do was not have separate sequential and parallel runtimes for OCaml. This is different from what GHC does with its threaded runtime for parallel execution. As a direct consequence of this, we had to ensure that our existing sequential programs that ran on OCaml 4 ran with the same time and using just the same amount of memory on this new runtime. Right? This is a tall order, and this is what we set ourselves. So the primary work in designing like a parallel language, which is a high-level language, is that you want a parallel allocator and a garbage collector. So we went for a design which is particularly not novel, but it ensures that your allocations and garbage collections can be low latency. So in this design, our units of parallelism, which is domains, each had its own minor heap into which new objects are allocated. And then when the minor heap is done, every survivor is promoted to the single shared major heap. And we had some restrictions between the pointers between minor and major heaps. We allowed pointers between minor and major heaps, but we did not allow pointers between minor heaps originally. So in this design, if one domain would like to access an object in another domain's minor heap, it would make an RPC call asking that remote domain to promote that object. The target domain would promote that object and respond to the call with the new location of the object in the major heap tab. So this design is nice. It has some nice properties. In particular, you could independently garbage collect each of the minor heaps without having to stop all of the domains. Our major collector was a mostly concurrent mark and sweep collector, which had very short stop the world sections. And the idea is that this particular design ensures that the GC latency remains low, and you can scale with additional domains. So fairly quickly, we were able to bring one up, and we spoke about this experience in OCaml 2014. Right? But we were actually building upon a large sequence of prior art, right? This is not novel at all. We didn't want to go for novelty. We wanted to go for something that just works. So Damien Dollinger and Xavier Leva, in their Popple 93 paper, had a concurrent and generational garbage collector design for their concurrent camel light. Simon Marlowe and Simon Peyton-Jones had a paper in ISMM 2011 where each of the threads in GHC had its own local heap, and these could be independently garbage collected. But this particular design did not make it into the mainline because at that time, this particular GC could not compete with what was back then in GHC. So during my PhD, I worked on multi-Milton, a parallel extension of the Milton standard ML language. So one of the nice things that we had done exploiting this invariance between the heap is that you could take unmodified standard ML programs and run it on non-cache coherent Intel single chip Pro computer. This was quite nice. So recently, Umutakar's group at CMU has had a long series of work where in their Maple language, which is also an extension of the Milton standard ML compiler. And the cool idea there is that you arrange the heap in a hierarchy that sort of mirrors the fork join hierarchy that you have in your program. And you have this restriction where the only cross heap pointers that are allowed are to your ancestors. So no pointers are allowed between siblings or to your descendants or to the descendants of siblings. So a heap that has this property is said to be disentangled. And Sam had a distinguished paper earlier this week where they had this very fast check for entanglement detection. And Sam is also giving a keynote at the ML workshop later this week on how to do scalable parallel functional programming through disentanglement. I'm quite excited to hear this talk. So yeah, so given that we were building on a good tradition of building these GCs based on these invariants, we saw excellent scalability on 128 cores. It maintains low latency on large core counts. Importantly, this particular GC, if you only had one domain, it mirrors what OCaml had today in OCaml 4. So this mostly retains the latency, throughput, and memory usage characteristics of OCaml sequential programs. So we were all very happy. We thought we had something done and we can upstream it. Disaster. Right? So in order to enforce this invariance, we had to introduce read barriers into the language. OCaml did not have read barriers. So read barriers are essentially some check that you introduce just before you access any OCaml object. On the OCaml side, this is easy, right? This is probably a single instructions or two instructions that your branch predictor always correctly predicts. So the performance impact of this was very low. But in our design, GC read barriers were also GC safe points where the GC can run. OCaml has this wonderful CFFI where C programs can access the OCaml heap, and it is written in such a way that it assumes where GCs can run. And in particular, GCs could not run during an object read, but now they can due to this read barrier design. As an offshoot of this, what happened is that every program that uses CFFI had to be rewritten, right? And in particular, there was no push button fix for this. The OCaml compiler uses a lot of CFFI for implementing a lot of these features, and we had to struggle to actually get this feature right. And we could see that this is not going to be a scalable solution because every sequential program, every sequential library that uses CFFI will have to be modified, and there was no static check that can help you here. So we had to go back to the drawing board. So what we did was we relaxed the invariant that there could be no cross minor heap pointers. And because there are no invariants to enforce, we did not read a new read barrier. We also did not break the CFFI now. But because of these cross minor heap pointers, our minor collection is now a stop the world parallel collector. So our initial worry was that when we increase the number of domains to say 64 or 128, bringing all the domains to a stop for every minor collection would be very expensive, right? That was the motivation for going for a design where you could independently garbage collect each of the domains. It turns out that you can bring all of these domains to a stop fairly quickly. This is because of how frequent minor allocations are in OCaml. And every minor allocation involves a conditional check to see whether you still have space in your minor heap. And you can spuriously make this check fail and interrupt a domain and bring all the domains to a stop. So our original worry was unfounded, and we actually found that this design worked much better than our earlier design, which required an RPC. So we spoke about both of these designs and extended this to cover the awkward squad in a programming language, including weak references, ephemerons, finalizers, and so on, and with extensive evaluation in this ICFP'22 paper. The other major problem that one has to think about when introducing parallelism into the language is the problem of data races. When two threads perform unsynchronized access to a shared memory location, and one of those is a write, then there is said to be a data race in the program. So because of compiler optimizations and hardware optimizations, you may observe behaviors which you cannot simply explain as interleaving of operations from different threads, right? These programs are said to exhibit non-sequentially consistent behaviors. So one thing we attempted to do was to enforce sequential consistency to OCaml, right? What would be the cost of saying OCaml will always have sequential consistency even in the presence of data races? This turned out to be quite expensive for relaxed architectures. In our measurements, it was about 2x lower for sequential programs running on this new runtime because we wanted to enforce SC. Right? So we needed a relaxed memory model for OCaml. Luckily, we had the second mover advantage. So we were not doing this first. There were plenty of other language memory models that we could learn from. So if you look at languages like C++ and Swift, they have this very nice property called DRFSC, which ensures that if your program does not have data races, it will only exhibit sequentially consistent behaviors, right? But unfortunately, these languages do not define the semantics for in the presence of data races, so they may do anything, so they may also catch fire. But OCaml programs, well-typed OCaml programs cannot crash, right? So this particular memory model was not something that we could adopt for OCaml. Java memory model does better. So it has DRFSC, but it also ensures that under data races, programs don't crash. But Java memory model has this limitation that when you have a data race and you know that there is some point in the execution where you know the data race is done, you may still have the effect of the data race beyond this point. So we define this property as data race not being scoped in time, Essentially, you can't do modular reasoning in the presence of data races in Java. On the other hand, if you look at language like Rust, it ensures that there are no data races by construction, by extending the type system. We didn't want to do that at that stage because we wanted all of our existing programs to work. There is some future work here, but we chose not to do that at that point. So one advantage that we had with Multicore OCaml is that there were no parallel OCaml programs in the wild, right? This is unlike, say, C++ and Java, where you have these expectations of what the parallel performance should be, and you have these memory model people trying to sort of wrestle with the people to say, hey, can we add more safety here? So we didn't have to worry about all of that. We had a free reign. So we ended up designing a very simple, comprehensible operational memory model, which only has atomic and non-atomic locations. We had DRFSC, so data race-free programs remain sequentially consistent. We also do not have out of thin air values. Even in the presence of data races, memory safety is ensured. And we did not have any relaxed axes. So the model does not have relaxed axes. So our thinking was that if someone really wanted to extract that last percentage of performance from the hardware, they would implement that particular module in, say, C++ or Rust, write a OCaml wrapper, and be done with it. So vast majority of the programs can still remain in OCaml. Go, the recent update of the Go memory model in the version 1.19, which was released in August, attempts to go for this model. But in Go, very reasonable things like accessing interface values, strings or slices involve accessing multiple words non-atomically, and hence they have catch-where semantics there, right? So it's getting there. So the key innovation in our model is this property of local data race freedom, which allows us to do compositional reasoning in the presence of data races. So you could essentially prove some property about your library, and this property would not be broken while linking with a code that has a data race. And the performance impact of our memory model on sequential programs, it was free on x86, and it had less than 1% performance impact on ARM. So we wrote about a formal model of our memory model and its compilation to x86 and ARM in this PLDI 2018 paper. We believe that if you have a high-level language and you want to include a relaxed memory model, you may start from the OCaml memory model rather than, say, C++. Okay, so we always knew that parallelism is a performance hack. It's a resource. Concurrency is a language, it's a programming abstraction, right? So we always knew that we wanted language level threads in Multicore OCaml. So OCaml does have support for concurrent programming through LWT and async. These are monadic concurrency libraries. So one of the properties that these monadic concurrency libraries have in a language like OCaml is that they split the world into asynchronous and synchronous functions. So while asynchronous functions can normally call synchronous functions, the converse is not true. You have to have some sort of special calling convention to go the other side. And this was succinctly captured nicely in this essay by Bob Nystrom called "What Color Is Your Function?" So many languages, including JavaScript and Rust, have this particular issue. So our idea was to eliminate function colors with native concurrency support. So essentially, you can implement language level threads in two ways, right? You can say my threads, my schedulers, and the synchronization mechanisms are all implemented directly in the runtime. Or you can say my language exposes a lower level mechanism on top of which I can implement all of these concurrency libraries as a library, right? So GHC and Go implement thread schedulers in the runtime system. So you have thread schedulers. You also have concurrency mechanisms such as MVARs and channels implemented in the runtime. There are a few downsides to this approach, right? So in GHC, for example, these mechanisms are implemented in the language of the runtime, which is C, but not Haskell. These are complicated code. I would like to write all of these in Haskell. There is also the lack of flexibility. You cannot easily change the runtime system to change a policy. And the maintenance burden falls on the compiler developers in order to maintain this complex code. So back in 2012, I spent a summer at MSR Cambridge, where we tried to lift the concurrency substrate of GHC from the runtime and implement it directly in the language. So we were partly successful, but we ended up with this one particular deadlock. So the crux of the issue is that the thread scheduler in GHC interacts non-trivially with lots of other systems in the runtime system, including the lazy evaluation mechanism called black holing. So what black holing tries to avoid is that if two threads try to force the same thunk, you want to avoid recomputation. So you will pause one of the threads on this thunk and wake it up when the evaluation is done. So this requires access to the scheduler, but now our schedulers themselves are written in Haskell, which may themselves require to be suspended on a black hole. So we had this cyclic dependence, and there are probably ways around it, but we ran out of time. But for me personally, I think this takeaway was that once you add a feature into the runtime system, it is very hard to undo it, right? So when we started designing Multicore OCaml, we knew we were not going to implement all of these mechanisms in the runtime system. So in Multicore OCaml, we wanted to implement everything in the library. So obviously, you have to have some sort of first-class continuations. The question is which kind? So Carl Brugman and Ken Tibwig showed how to represent one-shot continuations efficiently in Shea scheme. And they also showed that you can express all sort of concurrency mechanisms just using one-shot continuations. In Multi-Milton, we had implemented an asynchronous and parallel extension of concurrent ML using one-shot continuations in Milton. On the other hand, Oleg Kislev told us that undelimited continuations, which are exposed by call CC, are a bad abstraction. And undelimited continuations do not occur in practice, right? So whenever you try to use undelimited continuations, not for compilation, but for writing these concurrency libraries, you eventually end up having to do a hack to introduce this delimiter, right? So the takeaway there was that we needed some form of delimited continuations. So at this point, Mattia Pretnar and Andre Bauer showed us their wonderful F language, which had support for algebraic effect handlers. So effect handlers are this modular mechanism for programming with user-defined effects. Operationally, for us, it gave us a structured form of programming with delimited continuations. With effect handlers, you can encode all sort of computational effects, including concurrency, which is what we were interested in. So one of the nice things that I found with effect handlers is that they are much easier to comprehend than compared to other delimited control operators. So I don't want to focus too much on the code, but the code on the left here is some OCaml code that uses exceptions, and the code on the right uses effect handlers. If you ignore the semantics for the moment, they are syntactically very similar. And the way I sort of explain effect handlers to OCaml programmers is that operationally they are very similar to resumable exceptions, where the computation may be resumed later, right? So this is sufficient for starting to program with effect handlers. And the other reason why they tend to be easier than other control operators like shift reset and control prompt is that you don't have to carry around this prompt, or you don't have to deal with answer type polymorphism, if you know what those mean. Andre succinctly put it as effect handlers are to shift reset as while is to go to, right? So we took effect handlers as a mechanism to expose one-shot delimited continuations in OCaml, and we spoke about this experience in OCaml 2015 workshop. Since then, there has been an enormous amount of work both on the type system side of effect handlers as well as the implementation side. They've also had impact on industry. So soon after my OCaml 2015 talk, I repeated the same talk at what was then Facebook to the React team. For those who don't know, React is this world's most popular UI framework that is used by 1 in 2 websites in the world. And effect handlers have had a direct impact on a feature in React called React hooks. This is due to no fault of mine. But the idea here is that React hooks are a mechanism to manage state and effects within React apps. Right? So it's nice to see impact in the real world. So unlike research languages like Coca, Effect, and F, effect handlers in OCaml do not come with an effect system. We don't actually track effects in our types. So they are much more Spartan. In fact, we don't even have dedicated syntax for effect handlers in OCaml. We just expose them as functions. And the idea is that I want to provide uh, room for syntactic innovation in a future implementation of effect handlers for OCaml that comes with an effect system. Our focus so far has been to say, I am going to add effect handlers into the language. I want to preserve the performance of legacy code. And I want to ensure that debugging and profiling tools such as GDB and perf continue to work when we add effect handlers to the language. And we've spoke about this experience in the PLA 2021 paper, where the focus is particularly on backwards compatibility and compatibility with tooling. So we've gone ahead and implemented high-performance direct-style asynchronous I/O library called EIO based on effect handlers. And EIO competes handsomely with the state-of-the-art in Go and Rust. Right? It outperforms Go and it gets close to Rust. We can do better. But really, personally, if I can write my high-performance code in OCaml and I'm within, say, 10% of the state-of-the-art, I would take it. So coming back to this notion of language level threads are making a comeback. So there is this project Bloom in OpenJDK, which adds five-verse continuations and tail calls to the JVM. There is work on adding typed continuations to model concurrency in WASM. And an exciting development is native first-class delimited continuations have been merged to GHC 2 days ago. Right? So we can actually go back and attempt to re-implement control.concurrent on top of this. Okay, so what are the takeaways from this Multicore OCaml experience if you were designing your programming language abstractions and you want to upstream it to some industrial strength language? Firstly, care for your users. Your users have limited time and patience, especially if they're not going to use your new feature that you are adding to the language. So for us, most code is likely to remain sequential even after we add concurrency and parallelism to the language. So the transition to the new version should be either a no-op or you build tools so that there is a push-button solution to make this transition. Of course, for us, it was not a push-button solution. We did have to break features at the edges of the language. So one thing that we did was build this tool called OPAM health check. So OPAM is this package manager for OCaml that includes all of the packages that you release on OCaml. So we OPAM health check, what it does is every week it builds the universe of OPAM packages on different compilers. Here I'm showing OCaml 4.14, which is the latest release compiler, and OCaml 5, whose alpha release is out now. So every green box indicates that that package builds. Every yellow box says that that package, a dependency of that package fails to build. And every red box says that that particular package is failing. So this is published online, and as a package developer, you can go and check, hey, is my package broken? And you actually get a log and you can go and fix it. Multicore OCaml team has also been proactive in going ahead and fixing many of the broken packages. If your programming abstraction will affect performance, you should rigorously, continuously benchmark your change on real programs, right? OCaml users don't just run synthetic benchmarks, right? They run real programs. So our attempt to sort of build some reality into our experiments is that we built this tool called Sandmark, which is a collection of real-world OCaml benchmarks, as well as benchmarking infrastructure for running these benchmarks. So we pick real-world programs from the wild, including Coq, Proof Assistant, Alter Go Solver, Ermin Database, which pulls in their large set of OPAM dependencies as well, right? We have around 50 of these, and we regularly benchmark them on these benchmarks, and all of our results are based on these results. So suppose I have a program P, and then I ran it on OCaml 4.14, it ran in 19 seconds, and on OCaml 5, it is 18 seconds. You have to ask yourselves now, right? Are these speed-up slowdowns statistically significant? It turns out that modern operating systems, architecture, and microarchitectural effects introduce a lot of noise at very small scales. Right? As an anecdote, while we were trying to benchmark our measure the overheads of memory model by inserting fences, we observed that I could insert fences into my sequential program and make it go 20% faster. Right? I only expect slowdown there. So then we replaced those fences with no ops of the same length. It was still 20% faster. Right? And then I took this program, ran it on a different Intel machine at a different generation, right? And this speed up was not anymore there. Right? Modern processors do a lot of magic underneath, right? And we can't see what this magic is. So our approach here is to essentially try to tune the machines to remove the noise. We also observe that we can report instructions retired along with real time in order to interpret the meaning of whether a particular speed up or slowdown is just due to noise or it's a real change. So we spoke about this particular experience in OCaml 2019. There is an accompanying write-up which I've linked from here, which shows how to tune a Linux machine for benchmarking. There is also this wonderful paper by Emery Berger in ASPLOS 2013, where they built a system called Stabilizer, where the idea is to remove the effects of memory layout on your programs. And they provide a number of statistical tools in order to do sound performance evaluation. If you care about performance, you should read this paper. So all of this is quite hard to set up this machine for tuned machine, and then you have to run all of these benchmarks. It needs a lot of compute. So we released Sandmark as a service, as a continuous benchmarking service. As a developer, you can just take your feature branch, point this at the service, and it will run all of these benchmarks on multiple tuned machines and produce the results in a nice UI where you can interactively explore the results. And this has been regularly used by OCaml developers every day. So the next thing that I want to emphasize is that you should invest in tooling. You should learn how to use tools, and if tools don't exist, you should build them. Much of my time during the early years of hacking on Multicore OCaml was debugging segmentation faults. So you'd have this program which will have 17 threads, which will fail once in 100 run reliably, right? And the point of failure, the crash, is far removed from the root cause of the bug, right? Even if you manage to capture this failure in GDB, there's no way to make progress because it's some crash, right? So here is where a tool like RR, which is a record and replay debugger on top of GDB, comes in very handy. So what RR allows you to do is to sort of capture this trace, but you can go from the point of failure backwards. So you can ask questions, and then you can keep asking questions backwards until you reach the actual root cause of the failure. RR is so good that if we manage to capture the failing trace once, we were guaranteed that we would fix that bug. Right? If you are using GDB today to do anything, you should switch to RR. The second tool that we built upon is this tool called Thread Sanitizer, which is now as part of the LLVM project. So Thread Sanitizer dynamically detects data races. It has been used for C++, Go, Swift, and other languages. We've used Thread Sanitizer for OCaml for detecting data races. Implementing efficient data race detector is a lot of work. We are just building on what is out there, and it's quite handy for us. The other thing that we put in a lot of work is tracing. Our initial tracing tool was a hacked up version of GHC's ThreadScope. ThreadScope is wonderful. This is an actual trace where we had annotated some issues that we had found. So this sort of visual debugging, eyeball debugging of performance problems is great when you have these tracing infrastructure. If you suspect there is a problem and you actually now look at a trace, the problem becomes obvious, right? So here we are looking at something where we say, hey, why is there such a long minor slice, and why is there another major GC cycle so soon? This would be very hard to do if you were reading like a textual log of traces, right? So this was quite useful for us, and we built multiple generations of these tools. And the current version that we have in OCaml 5 is we have something called runtime events, which does efficient CTF-based tracing that is always on, right? It's not emitting any trace, but that feature is always on. You can take any OCaml 5 program, enable a flag or send it a signal, and then it starts producing live traces. So you can live trace any OCaml program today. And Sarik and Patrick are talking about this particular tracing framework in OCaml workshop later this week. So it was quite a challenge maintaining a separate fork of the compiler for 7+ years, right? And we had to go through multiple tricky rebases in order to keep it up to date with the mainline. And in that process, unfortunately, there wasn't always communication between the features being developed at trunk and what we had, right? So we had to sort of drop certain features because we just couldn't understand how to fit that into the GC design that we had. We are slowly working towards adding them back in, but that is a process. In hindsight, it may have been easier if we had enough planning to have made smaller PRs to the language. So peer-reviewed papers definitely add credibility to the report, to the effort. So I sort of view peer-reviewed papers as a nice design document of a snapshot of the system, right? And of course, that's not reflecting what is there, but you can start there and then start reading thousands of lines of code. Our project has always been open source and actively maintained. Surprisingly, there has been a lot of academic users from our early days, and having users helps convince the YAML developers that this feature should be added. And we did build tools like continuous benchmarking and OPAM health check in order to allay the fears that when this feature is deployed in the wild, then due to some unrelated reason, a sequential program breaks. Right? So when I started working on Multicore OCaml, I thought I'd start at OCaml 4. I would linearly hack on something. At one day, I'll be at OCaml 5. But it really turned out to be this asymptotic progress towards OCaml 5. And when I'm 90% done, this is when I would write the paper, right, get my artifact evaluation badges, and be done with it. But really, the rest 10% takes the 90% of the time. And while the first 90% could be done with few researchers, it turns out that you require a lot of engineers for the rest 90%. So the research was primarily driven from University of Cambridge, IIT Madras, and Jane Street. And today, OCaml core team, engineers from Tarides, and a lot of independent contributors have been working on getting the language across the line. So where do we go from here? Obviously to the moon, but how do we get there? So the first obvious thing might be that, hey, you should add an FX system to OCaml, right? But it's a lot of work. In a language which is as large as OCaml, you have to think about interaction of whatever feature you're adding with the polymorphism, modularity, and generativity features that you have already in the language. And then you have to do it in a backwards compatible manner as well. This is quite a tall order. I'm not an expert on FX systems, but I'd be very happy if somebody took this up. OCaml has a very nice compiler to JavaScript. But we can't compile effect handlers yet to JavaScript because we don't know how to compile delimited continuations efficiently to JavaScript. Daniel Hillestrom and others have published papers where they show how to take different variants of effect handlers and compile them efficiently to untyped lambda calculus. There is some work there, but JavaScript engines are their own beasts, and hence there needs to be a lot of engineering work there to get the right compilation strategy. So there is some exciting work going on within Jane Street. Stephen Dolan and Leo White are adding modal types to OCaml. In particular, they're using this feature to allocate values on the stack, and then using the type system, ensure that these values do not escape the stack frame. Okay. So we can, one cool idea is that you can take untyped effects and use these modal types to get lexically scoped typed effect handlers. Right. This would be much easier. You would get FX system here, but you don't have to have the full power of tracking FX in types. And this might be more backwards compatible than a full-fledged FX system. Overall, right, OCaml is getting a lot of performance-oriented features that are currently being developed or in development, including parallelism in OCaml 5, avoiding heap allocations through modal types, unbox types, which lets you tightly control the memory layout, and flambda2, which is a aggressive optimizing compiler for OCaml. And when all these features land, right, OCaml would be a language where you can have Rust or C like control and performance while having GC as a default and have the ergonomics and safety of classic ML. I'd be excited to see what we can actually build with this language. So Richard Eisenberg, Stephen Dolan, and Leo White are talking about the unbox types work at the ML workshop tomorrow. With that, I'll stop here and enjoy OCaml 5.